before, isn't it?
How's everyone doing? Main plan for today is to continue on with sound, looking at kind of the physical nature of sound and a few related concepts. Pretty conceptual based day overall. I'm going to talk mostly about some things about sound and waves that I think everyone should know, and then a little bit of math tied into it. We'll end today looking at least beginning the last math thing, and we'll practice that mostly on Friday. Any questions or needs or concerns, anything at all from you guys before we get started? All right. And let us continue on from Monday. As we began chapter 10, we started looking at some base definitions and vocab terms for waves and also simple harmonic motion. I'd say two of the vocab words we're going to revisit today are wavelength and frequency. Specifically, the wavelength is, again, the physical size of a wave from start to finish, and frequency is how often that wave strikes something or passes something while it's traveling, measured in units of hertz. We looked at how frequency and wavelength tie into wave speed. All waves are made up of traveling energy, and that energy, since it's traveling, has a specific velocity. You can calculate the velocity of that wave and therefore that energy by multiplying its wavelength and frequency together. And that all waves of the same type have the same velocity as long as they are traveling through the same medium. We looked at some standing waves that I generated on this machine. Where do I have this tuned to earlier? There we go. And so this wave, since it's the same type of wave and the same medium, would have the same velocity as this wave, even though it's a different frequency and a different wavelength. It's just the same speed as long as it's the same type and the same medium. And today we're going to apply some of that knowledge to specifically looking at the nature of sound and how humans perceive sound. A little bit about light as well, just given that it is also a wave and humans also perceive it. Questions before moving on? All right. Now, before we look at, well, let us define what sound physically is first. We've talked about how waves are traveling energy, and so that means that sound is traveling energy. When you speak, you put energy into the air, and that energy travels through the air, entering someone's eardrum. That causes their eardrum to shake, and that sends signals into their brain, which they perceive as sound. Now, the precise mechanism through which sound does this depends slightly on the structure of sound versus other wave types. There are two main classification systems for sound, for waves. Sorry, apparently I need more water. There are two main classification systems for waves. First is their shape. Second is their structure. We're going to look at the classification systems to figure out what type of wave sound is classified as to compare it to other types of waves like light. First is wave shape. Different waves have different shapes based on what direction they make their medium vibrate in. The wave currently seen from this standing wave machine right now, and again, this is sort of the classical shape people tend to think of for waves. This is called a transverse wave. So all waves of this shape, like ocean waves and the wave you're currently seeing, are called transverse. And a transverse wave simply causes its medium to vibrate perpendicularly to the direction of travel. The energy is traveling through this string back and forth in the x-axis, Meanwhile, the string itself is vibrating perpendicularly to that in the y-axis. So the definition of a transverse wave is the oscillation is perpendicular to the direction of travel, and as a result, they tend to look like this when they are moving horizontally. The kind of shape that you tend to think of. This is not what sound does. This is not a sound wave. Light looks like this, but sound does not. Sound is the other shape. Sound is a longitudinal wave. And a longitudinal wave, to kind of, where's my spring? To contrast with the transverse wave. Transverse wave, the medium oscillates perpendicularly to travel. For a longitudinal wave, the medium vibrates parallel to travel. So I'm going to leave the transverse wave going, and now I want you to instead, for the longitudinal wave, focus on this spring. For a longitudinal wave, if the spring is the medium has to vibrate back and forth in the same axis as the energy travels in. So I'm going to pluck this spring in such a way that the energy is going to travel x-axis, left to right, back and forth, and the spring has to vibrate in the same axis. So I'm just going to pull back on one of the coils and send a pulse down the spring. The spring is vibrating in the same axis the energy travels in. And that is what sound does. Sound is a longitudinal wave, not a transverse wave. This means that sound is basically a little pressure pulse. When you speak, or make any noise really, you put energy into the air. That causes the energy to move, because if something has energy, it wants to do something with it. Air will vibrate and move once it has energy in this form, bless you. And when the air has that energy, it will move, it'll kind of create a little vacuum pressure pulse, and that pulse pushes outwards and forwards in the same direction it travels in. Kind of like a ripple in like the surface of the water if you throw in a rock. The water will pulse outwards and then also travel outwards in the direction of that pulse. Sound does the same thing. You just can't see it. Although, I suppose if you filled a room up with smoke or dust and turned on a very high power speaker, you might be able to see it shake like this. But I don't have the budget for that, unfortunately. Now, bless you. There's a second wave classification system. First, we can talk about the shape of the wave. And second, you can talk about the structure of the wave. We talked briefly on Monday about the medium that a wave travels through and how its speed depends on the medium it's currently traveling through. The medium, if a wave is traveling through a medium, that medium is just the physical material, solid, liquid, or gas, that the wave is currently traveling through. And the next classification system for waves refers to the medium that they are currently using. The first classification was wave shape, transverse and longitudinal. The second classification system is structure. Does the wave require a medium or not? This classification system sorts waves into mechanical waves, which require a physical mechanical medium to travel through. It doesn't have to be solid, it can be liquid or gas. It just has to be made of matter, and the wave has to be able to travel through it. Mechanical waves require a physical medium, and this is contrasted to electromagnetic waves, which don't require a medium to travel through. You ever heard how you can't hear in space? Sound doesn't travel in space. That is because there's no air in space. There's no nothing in space, except a very fine, thin layer of particles that's too thin to do anything with. Since space is a near-perfect vacuum, there is no medium for sound to travel through, therefore you can't hear in space. This makes sound a mechanical wave. Sound requires a medium. If you have ever perceived a sound wave, it has been either through the air, the water, or the ground. Those are all mediums. You can't perceive a sound wave through the vacuum, and that is why there's no noise in space. To contrast this, light is an electromagnetic wave because light does not require a medium. Electromagnetic waves are literally made out of electromagnetism. We'll learn about that a bit more if you stick around for 1510 next semester. But since EM waves are kind of self-contained, literally they're photons, little packets of electromagnetic radiation traveling in a straight line through the void of space. And since they don't need a medium, they kind of make their own bodies out of electricity and magnetism. They don't need a medium, they can travel through space. And that's why we do get light from the sun, but not noise from the sun. Make sense? It's a good thing we don't get noise from the sun because the sun is constantly a raging inferno, and if we could hear that, it would drive us insane. So, since sound requires a medium, it is a mechanical wave. So the full classification for sound is it is a longitudinal mechanical wave, describing both its shape and its structure. Light, to contrast, is a transverse electromagnetic wave. Basically, the exact opposite in pretty much every way except base wave behavior. And because they are so physically different, that is why you have two different sets of organs to detect the two of them. Your ears work by absorbing physical mechanical sound waves from the air. Your eyes, meanwhile, need different receptors that are able to absorb radiation. And creatures that live underground don't have eyes because no light passes through the solid objects. They just use ears. So, light is a longitudinal mechanical wave, and we're going to continue to talk about its properties and structure for today. Questions so far? All right. So, sound is longitudinal mechanical. It requires a medium. Your ear is designed to hear in air. There's literally air in your ear. And even though sound travels faster underwater, your ear is just not designed for that. So you very rarely can ever hear clearly underwater, even if the sound does hit you faster. I think I've mentioned already that more aquatic creatures use echolocation because the sound travels faster down there. It's more reliable in water than in air. And humans perceive sound primarily through two different measurements. Humans perceive sound mainly through a combination of intensity and frequency, or pitch. We'll talk about intensity first because it ties into the longitudinal nature of sound waves. Intensity is basically volume. Sound intensity is just volume. The more energy you put into the air, the more energy enters your ear, the more intense your ear is vibrating, because your eardrum is like a physical drum. When sound waves beat on your eardrum physically vibrates to that frequency, and as a result, your brain perceives that frequency. So your eardrum literally has to shake and beat like the surface of a drum, and that's why if there's a hole in your eardrum, you don't hear as well, if at all. The intensity of the sound, literally the amount of energy in the air, correlates directly to the strength of those vibrations, and therefore humans interpret that as volume. The more intense, the more energy, the bigger the volume is. I'm going to tab to a different slide real quick that's going to show a representation of the sound wave coming from a handgun being fired, just to kind of represent the physical boom emanating out from the explosion. So just to preface that, this is kind of a freeze frame representation of that vibration. And what's happening here is there's literally an explosion going on in this guy's hand. That explosion puts a lot of energy into the air, and that energy will travel through the air as a sound wave. That energy, when the air has it, it's going to be very highly concentrated right near this guy's hand. And as a result, the sound will be loudest nearest this guy's hand. I kind of compared longitudinal waves earlier to throwing a pebble in the water and seeing the ripple, right? This is a three-dimensional ripple through the air. Basically, the explosion is the rock hitting the water's surface. The ripple is going to echo out from that point, but three-dimensionally in all directions instead of just across 2D water's surface. And that ripple is interesting because, one, it is a longitudinal pressure wave. When the air has the energy, it's going to shake. Its pressure is going to kind of instantaneously change, and that pressure wave travels out in all directions, vibrating in the same direction as travel. So it's a pressure pulse in all directions. And it's loudest nearest the explosion because literally that's where the energy is most compressed into the smallest volume of air. The second it starts traveling outwards, the pressure kind of is forming a big sphere, and it is a sphere again, it's not a flat circle, it is a sphere. And that sphere constantly expands as the wave travels outwards. If the blast puts 1,000 joules of energy into the air, that 1,000 joules is initially very highly concentrated, but weakens the further out it goes because it's now affecting a bigger surface area of air. So the further out the sound wave goes, the more spread out and thin that energy gets, and that is why sounds get weaker the further away from the source they are. So you knew that, I'm just describing the physical principle behind it. I'll note before moving on, we measure volume using the decibel scale, and I just want to point out that decibels are logarithmic in nature. Most sounds you deal with might be, about 30 decibels. 40 decibels is not, like 40% bigger. It's 10 times bigger. Decibels are a logarithmic scale base 10. If a sound is 10 decibels louder, that means it is 10 times louder, and there's 10 times more energy being funneled right into your eardrum. This is why exponentially louder sounds hurt more and more and more. So, logarithmic scale. Doubling the decibels doesn't double the volume, it would increase it exponentially, so take care of your ears. Questions about any of that so far? All right. The other method that humans use to perceive sound is its pitch, which physically translates to frequency. We talked about frequency. The frequency of sound is literally the pitch of sound you can hear. Low frequencies are low pitches, high frequencies are high pitches. And the frequency of the sound wave literally affects the frequency that it makes your eardrum shake, and that affects the frequency of the electrical signals going from your drum to your brain. And we've mentioned that as long as the speed of a wave stays constant, each frequency is going to have a specific matching wavelength to create the same speed, right? Every wave that I put onto this string, no matter what frequency that is, will have the same speed as long as it's the same string, even if I change the frequency. But if I double the frequency, I would cut the wavelength in half to make the same speed. This means every sound frequency, every pitch, has a specific matching wavelength as long as the speed of sound remains unchanged. So specific pitches not only correlate directly to the frequency, but also have a matching wavelength. And those different wavelengths matter to how humans perceive sound. Let's do some sample math. I have on the board right now a sampling of different frequencies that different humans are capable of hearing. We're going to treat the speed of sound as a constant 343 meters per second right now for simplicity's sake. That's the speed through room temperature air at standard atmospheric pressure. And I've picked 3 specific frequencies. I would like you guys to quickly work on your own and amongst yourselves to find the corresponding wavelengths of all of these frequencies while I talk about the significance of each one. First is 20 hertz. This is the lowest frequency of sound that the human eardrum is often capable of perceiving. Any frequency lower than that, your eardrum does not beat fast enough for your brain to be able to notice the electrical input. Any lower than 20, you can't do it. And frankly, even then, 20 is still really hard to pick out. right now, this speaker is putting out 20.6 hertz sound, and I hear the physical rattling of the object more than I hear the sound wave. I can increase it to 100 hertz. And now I can kind of hear the sound more than I just hear the rattle. But if it goes much lower, it's a lot harder. Frankly, at this point, I'm feeling the vibration through the desk more than I'm hearing it, and it's at 60 hertz. But 20 is, statistically speaking, the lowest that humans can hear. What wavelength would 20 hertz sound have? Correct. 17.15 meters. And that unit does come out as meters because for speed of sound you plug in meters per second. Hertz is 1/seconds, so you end up with meters out the other side. So just for a little bit more context, I'll convert that into feet real quick. 17.15 times about 3.3. That is a wavelength of 56.6 feet. So if you are hearing 20 hertz sound, that means that a pressure wave about 56 feet long is striking your body. That's disrupting a lot of air. And that's a very big physical vibration that is transferring into your body. Low frequencies correlate directly to big wavelengths, and those big wavelengths, low frequencies, correlate to bass tones. Bass in music is literally low frequency, high wavelength sound. And have you ever noticed that if a speaker has the bass cranked up, you can kind of feel your body rattling? At least I feel it that way. Like sometimes it feels like my chest is shaking and my teeth hurt. Does anyone else get that? Or am I just too sensitive to noise? See a little bit of nodding. So, those bass tones make your body rattle because of these giant wavelengths. There is a big air vibration physically striking your body, and when the frequency is that low, when the vibration is that big, the energy doesn't just transfer into your eardrum, it can transfer into your whole body and make your whole body shake. So that is why bass can make your teeth rattle. Sometimes I feel it in my chest, it gets too loud. I'm bringing this up to point out the phenomenon of infrasound and why it is dangerous. The lowest frequency humans can hear is 20 hertz, and even then it's still kind of difficult to. Any frequencies lower than that, from 1 to 19, are called infrasound. Infra is just the prefix for low, so it's sound that's too low for humans to hear. Infrasound can also make your body vibrate and rattle because its wavelength would be even bigger. Drive down the frequency, drive up the wavelength as long as speed stays the same. So the wavelengths for infrasound are even bigger, so they can make your body shake even more. And the problem with infrasound is you can't hear it. So you don't know if it's hitting you until it starts doing something to you. And infrasound can make humans sick and possibly kill them if you're exposed to it for too long, because it is going to make your entire body vibrate and get nauseous and eventually scramble your brain. For this reason, some people have invented infrasound weaponry that can hurt people, and that is not good. So, avoid infrasound if at all possible. On a less awful note, some house hauntings have been attributed to infrasound. Since infrasound is too low to hear, you don't know it's there, so you can't hear it. There's no immediate detection in your brain. But if you're exposed to it, it can start making you feel ill and doing weird things to your head. So low amounts of infrasound can sometimes cause paranoid haunting phenomenon in the human brain. And some haunted buildings happen to be putting out infrasound vibrations. So ghosts are real if you consider the infrasound themselves to be the ghost. It's sometimes just infrasound. So, on the one hand, infrasound, it's weird. Just try to avoid it if you can. Avoid haunted houses. Now, the next frequency listed up here is 6.25 kilohertz. That is a potential average human voice frequency. And what would the wavelength for that be?
I got 0.054.
Very good. You caught on to the kilo prefix, because you would want to convert that into base hertz before using it, and that's going to give you a much smaller wavelength. The bigger the frequency, the smaller the wavelength, and you do have to convert kilo to base before you use the formula. So that is one wavelength that might strike you if a human is talking to you. Now, if you've ever done anything with music, you probably know that most of the time what you're hearing is a combination of frequencies. Because if you play one pure frequency, it's just a tone. It's not usually very comfortable to listen to. So music and even human speech is always a combination of frequencies. My own voice, even if I try to make one solid tone, is multiple frequencies at once based on the different parts of my voice box vibrating at different frequencies. So no human speech is ever one frequency. It can range from 2,000 to like 13,000, just based on the individual. So I picked one average for simplicity's sake, but human speech is very complex in terms of the frequencies involved, as is music. And this is the atypical sort of wavelength. Most sounds you'll ever deal with have very small wavelengths, which is good because big wavelengths do weird things to you. So this is just sort of an average of the types of sound you'd expect to hear on a daily basis. The last number I put up here is the highest frequency any human has ever allegedly been able to hear, 20 kilohertz, 20,000 hertz. That wavelength is even smaller, 17 centimeters. And that is the highest that it goes for the human perception of sound. And even then, if you were ever able to hear that, it would have been when you were a newborn. Because every single second you are alive after that, all of your cells are aging, including the cells of your eardrum, and they become less tuned to high pitches of sound. The older you get, literally the worse your hearing gets, because the top frequency you can hear drops. I'd wager a guess that most of you guys, the top frequency you'd probably be able to reliably hear is like maybe 16,000 hertz. And for me, it's lower because I'm older and because my earphones are too loud. So take care of your ears. Frequencies higher than 20,000 hertz are called ultrasound. Ultra just reading the prefix for big or high, so it's just high frequency sound. And unlike infrasound, this does nothing to us. Ultrasound is harmless because the much smaller wavelength doesn't hurt you. It's big wavelengths that hurt you, not big frequencies. So ultrasound is totally harmless to human beings. Your eardrum just physically can't vibrate fast enough to perceive it, so it just does nothing to you. And that's why this is the type of noise we shoot at babies. This is safe for babies. This kills people. So that is why ultrasound is higher than 20,000 hertz. For comparison's sake, I put the, nope, that's decibels I want. That's the one. For comparison's sake, I also listed the hearing range for dogs in comparison to humans. They hear 40 to 40,000 hertz, and that's why dog whistles work. There's higher frequencies they can hear that we can't. Dog whistles are tuned to like 30,000 hertz. You can't perceive it, it doesn't hurt you, but the dogs get it. What I find interesting though is that the dog range starts after hours. So there's a band of 20 hertz of low frequency we can hear that they can't. So if you want to make a human whistle, set it to 30 hertz. And this pairing of wavelengths and frequencies is also true of light. Light is physically a different type of wave, but it's still a wave, so its wavelengths and frequencies are still paired based on the speed of light. This right here just lists the, bless you, comparisons of various wavelengths for different colors of light to their corresponding frequencies. But because the speed of light is enormous, 300 million meters per second, the differences between the two get pretty crazy. Frequencies of light, you can see, the frequencies are in the terahertz band, and the wavelengths are in the nanometers band. So they're teeny tiny and they move very fast. And even then, there's other types of electromagnetic radiation that you just can't see. It turns out every type of radiation is the same thing as light, and all that's different is the frequency. They all have the same speed, they just have different frequency wavelength pairings to create the same speed. So light is the same thing as radio waves and gamma rays. So your phone is irradiating you, but thankfully radio waves are harmless. But light is also radiation, so the sun is irradiating you as well, and you needed to see. Questions about any of that? All right. Now, frequency and wavelength aren't the only things related to speed of sound. Speed of sound also varies based on the medium that sound is traveling through. Since sound is a mechanical wave, sound requires a medium, and the properties of that medium affect the speed of sound. I've already mentioned that it moves at different speeds through different materials, but even the same material creates different speeds at different temperatures. The speed of sound through air changes based on the temperature of the air and also its pressure. But we're going to keep pressure constant today for simplicity's sake. The formula for determining the speed of sound in air is listed on screen right now. Sound velocity equals 331 times the square root of current temperature divided by 273. The 273 is there because this formula requires kelvins. And so for current temperature, you want to use kelvins so that it cancels out with the kelvins down here. And all this formula really does, it's taking the speed of sound through freezing air, which again, 0 Celsius, speed of sound is 331. It's taking that initial freezing speed and just scaling it based on the temperature changed from freezing. So you can use this to find the speed of sound at any temperature air, assuming pressure remains constant. And overall, again, if pressure is constant, and if humidity is constant, speed of sound is slower in the cold and faster in the heat. I am presuming that the higher temperatures cause the air molecules to be moving around more quickly, which causes them to physically knock into the next air molecule faster to transfer the sound through more quickly. Let us apply this principle to a trick that you might have heard of before. You ever heard that you can figure out how far away a storm is by counting the seconds between seeing lightning and hearing thunder? We're going to put some math to that, and we're going to tie in figuring out the speed of sound before doing it. It's a hot summer day. The temperature of the air is 32 degrees Celsius. And we see off in the distance a lightning bolt, and 6.4 seconds later, we hear the thunder. Note that you usually tend to see things before you hear them because light travels faster. The speed of light is 3 million meters per second. The speed of sound is usually 343. So light's about 1 million times faster. Therefore, humans tend to perceive light travel as basically instantaneous. Your brain's just not fast enough to notice it. So we're going to treat the light from the lightning as instantaneous, and we're going to figure out how long it takes the distance the sound has to travel to reach you in 6.4 seconds. So we counted the time that it took the sound to reach us, and we want to figure out the distance the sound travels in that amount of time. To do that, you need to know the speed of sound on this particular warm summer's day. 32 Celsius is very warm, in my opinion. Now, as long as the air temperature remains constant, the speed of sound doesn't really accelerate. The only reason sound should be accelerating is if the temperature is rapidly changing from start to finish. So as long as the temperature and therefore the speed remain constant, you can use Formula 1 to just describe the distance sound moves in any given amount of time. Same's true for light, it's just really fast. So as long as you know the time it takes and the velocity, you can figure out the distance the sound travels. So we just have to adjust the speed of sound based on the temperature first. So, speed of sound is 331 times the square root of current temperature over 273. What are we going to plug in instead of 32 degrees Celsius?
305.
Very good. 305 Kelvin. If you haven't written it in your note, well, I haven't asked you about temperature yet this semester, but if you need to write it in your notes, this is the Kelvin Celsius conversion. You just add 273. So, instead of 32 Celsius, we plug in 305 Kelvin, and that, from my recollection, should give us a slightly elevated speed of sound of about 350 meters per second, slightly faster on a hot day, compared to room temperature 343. Any issues with this? All right. Once you know that speed, you can figure out the distance it traveled in a given amount of time. In this case, 6.4 seconds. And again, by my recollection, that should give us approximately 2,236 meters, about 2.2 kilometers. Oh, 39. And that is meters. For a better, I guess, you can convert it to kilometers and that'd be 2.2, so several miles away. This particular storm you are probably pretty safe from, as long as the time between thunder and lightning doesn't get much smaller. So just putting numbers to that old trick. Any questions? A couple things to note. One, since sound is faster in hot air than cold air, note that if it was a winter day instead, the storm would be even closer because it would move, the sound would move less distance in the same amount of time. So just keep that in mind if you're watching thunderstorms in summer versus winter. Two, I just like talking about electricity, so if you'll humor me for a minute, I want to briefly mention why thunder happens in the first place. If you stick around for Physics 1510 next semester, that's when electricity comes up. And lightning is physically happens if electrons just flow out of the sky and into an object on the surface, and all those electrons have to travel through air, because it's not just empty space between the sky and the ground, there's air molecules there. And when electric current flows through air, you get plasma. So, same thing as in these light bulbs, actually. And since plasma tends to glow, that's why you can see the lightning bolt. You're not seeing electrons, you're seeing light given off by plasma. The light hits you pretty much instantly because it's too dang fast for a human to track. But when the plasma is made, since it heats up, it flash expands and makes a little sonic boom. So it takes up more space than it's supposed to, it expands and pushes air out of the way, likely faster than the speed of sound, and so it literally creates a sonic boom, and that is the thunderclap that echoes out from the source. So that's why thunder exists in the first place. There's another speed of sound trick that people sometimes use. And so we'll do one more quick example related to it. Namely, I want to make sure you notice a certain catch-22 if the word echo pops up in your homework. Have you ever seen a movie where someone screams into a cave or possibly drops something into a hole and listens for the echo to figure out how deep the cave or how deep the pit is? So we're going to put numbers to that too. I'm going to use the cave for simplicity's sake. Scream in a cave, you send sound waves in, and they'll bounce most strongly off of the flat back of the cave. So you can listen for when the echo comes out most strongly to figure out how far back in, how deep into the cave the back wall is. This particular day is not summer, it is very cold winter. It is freezing, 0 Celsius. So the speed of sound on this particular day is actually just going to be 331 because 0 Kelvin is 273, so the whole square root thing just kind of goes away. So the speed of sound on a freezing day with constant pressure is 331 meters per second. So 331 equals the distance the sound waves travel divided by the 2 seconds it takes you to hear your own echo. So in those 2 seconds, the sound waves travel 662 meters. Is that the depth of the cave?
No.
No, why?
Sound takes time to travel.
Yes, it took time to travel in, and then it takes more time to travel back out. Those 2 seconds weren't the time it took the sound to reach the back wall. Those 2 seconds were the time it took the sound to hit the back wall and then also travel back. So this 662 meters is double the length of the cave. It's the distance in, followed by the distance it also has to travel to get back out. It's like if you run down a football field and run back, you ran the length of the football field twice. So if there is an echo involved, you got to cut something in half at some point. Want to make sure you're aware of that. Make sense? All right. Overall of the concepts today felt cool. I aim for things to be understandable. We've got one more sound-related concept we're going to cover this week, and we'll introduce it today and do the math for it on Friday. The final is just kind of weird looking, but I want to at least make sure you're, in the time I've got left today, that you understand the concept before we do numbers on Friday. The last concept is called the Doppler effect. Have you ever heard that term come up before? All right, cool. Growing up, I heard it most often in like Doppler weather radar, and it turns out all radar and sonar technology uses this basic principle, namely if it's detecting the velocity of your target. In more common terms, just based on things that you would notice with your human ears every day, you ever noticed how if a vehicle passes you, whether or not it has a siren, the sound you hear changes pitch as it passes? I'm going to do a very bad impression real quick. You all heard that, right? Has anyone not heard that? Okay. Most any fast object will do this. Vehicles moving past you, even if they don't have sirens, just displace enough air and rattle enough to make the noise required for this. But as it passes you, it feels like you're hearing a different pitch, right? The frequency changes. But the frequency the object should make doesn't depend on where it is compared to you, right? Any given object should make the same frequency over and over again, right? If it's an ambulance passing you, the ambulance is designed to make the same pitch repeatedly. It isn't programmed to change based on where you're standing. It should make the same pitch repeatedly, and yet you hear a different pitch as it's approaching versus as it's moving away. I'm talking about why that is.
Friction. the air?
Not really this time. I know friction is commonly a source of issues for us, but it doesn't specifically involve friction this time. I'm going to draw a very quick and poorly drawn image of an observer and an ambulance both standing still. Nothing's moving yet. So right now, you're standing still. The ambulance has its siren on, but it's not driving. So the frequency you're hearing should be the correct pitch for the ambulance's siren. And since the speed of sound is considered constant, this frequency should have a specific corresponding wavelength, right? And that means all of these sound waves exiting the siren should have the same wavelength, they should be the same size, and therefore they should be the same distance apart from each other. Say the wavelength was 2 meters long. The ambulance makes one sound wave, it travels 2 meters in a very small amount of seconds, and at that point, the ambulance makes the next one. So all the waves, if the wavelength is 2 meters, all those waves should be 2 meters apart. Sound good so far? Now something weird happens once the ambulance starts moving. Because while the ambulance is moving and its siren is turned on, it's tuned to what's supposed to be the same frequency. Once it starts moving, it starts trying to catch up to the sound waves it already made. It's not able to literally catch up and pass them, because if you can do that, you're making a sonic boom and then you have a different problem. So the ambulance isn't going to catch its sound waves, but it's going to be closer to the ones it already made. So say you make a sound wave, then you hit the gas. So you make a wave, you hit the gas. Normally, the sound wave you just made should be 2 meters away before the next one comes out. But if you're moving towards the sound wave you just made, you're going to be closer to it when the next one comes out. Does that make sense? A weird kind of similar analogy would be like there's a lot of machines in factories that are designed to, like, you know, extrude like cookie dough or hot metal onto a moving track at a certain rate. And so it plops out a piece, the track moves on, it plops out the next piece, and the track is just constantly moving, set to a certain speed. If you turn the speed up higher, the objects kind of end up getting smushed together because the material is getting extruded to, like, it's getting bunched up faster and faster, right? Versus if you turn it too slow and the object ends up blorped out longer than it's supposed to be. The same thing is actually happening to the sound waves. Because if the ambulance is moving towards the wave it's just made, it's going to be closer when the next wave comes out. So instead of the waves being 2 meters apart, they might be 1.5 meters apart. And that drives down the wavelength. Like, the speaker's trying to make the same frequency of sound, but because the ambulance is now moving towards the waves, the functional wavelength keeps getting reduced because the next wave is getting made before the first one is fully finished. And so the waves get bunched together, like if you turn the speed up on the assembly line. That makes the wavelength smaller and the frequency bigger. We noticed earlier that smaller wavelengths correlate to bigger frequencies. So as the ambulance approaches you, the wavelengths get bunched together, the frequency goes up, and therefore the siren will be at a higher pitch than it's supposed to be while it's moving towards you. And that's why it's got a higher pitched whine until that moment it is at your position. That's the part. But then once it passes you, the opposite happens. Because now it's moving away from you, and that means it's also moving away from the sound waves it already made. So instead of getting closer to the waves it already made, now it's going to get further away from them, and that's going to drive up the wavelength. So it's getting further away than it's supposed to before making the next one. And that's going to make the wavelength bigger because now they're being forcibly spaced out. And a bigger wavelength correlates to a smaller frequency, lower pitch. And that's the part. And that is the Doppler effect. That's why that happens. And we will look at the formula and do math for it on Friday. Questions? Comments on the awful impressions? All right. Let me know if you need anything, any questions about any of this information or upcoming exam, and have a great day. Yeah, that's fine.